How's it going, everybody? Welcome back to another video on the classical particle system series. We are going to be considering constraint forces in this video. So let's assume that a particle is constrained on a path. We can just make this path arbitrary and generalize it as much as possible. I'm going to say that we're going to parameterize the path with respect to lambda here. So lambda is going to be our parameter. So x and y are going to be both functions of lambda. We're going to have a particle constrained somewhere along this path here. And we're going to say it's going to be subjected to the force of gravity. And of course, that's going to just be equal to negative mg y hat. So the negative and the y hat denote the direction, hence the vector is pointing down. But we also know that there's going to be another force. The gravity is not just going to be the only force, because if gravity was just the only force, then this particle would just be basically free. We know that if a particle is constrained, it's going to have a constraint force, right? And that constraint force is always going to be normal to the path that it travels. So here we can denote this as the normal force, or the constraint force. And the constraint force will always change to constrain the particle, of course. So for example, let's say let's put your arm or your hand onto the desk, right? And you push against the desk. The desk is going to push back. No matter how hard you push against the desk is always going to push back with equal and opposite force. That's going to be the normal force, or the constraint force, trying to keep that hand still, right? Otherwise, if there was no constraint force, your hand will just pass through the desk. As you can see, so the idea would be to, how do we split this force, this gravity force, into two components? So we're going to obviously have the tangential component of gravity, and this tangential component is going to contribute entirely to the motion of the particle, because we know the normal component of gravity is just going to be canceled out perfectly with this normal force. So that's going to be the idea. Let's figure out a way to split x hat and y hat in terms of the tangential component. So we can call that just t hat, and the normal component. So what I'm going to do is just get rid of all this so you understand the free body diagram. Pretty sure. So this is our particle. We can color that red. Our particle is just sitting here. And what we're going to do is split up these components that depend where it is on the path, of course. And we're going to write this t hat, and we're going to write this n hat. So t hat and n hat are both perpendicular to each other, or they are orthogonal. So their dot product would be 0. And they're also unit vectors, hence the hat notation. So their magnitude would be equal to 1, always, no matter where it is along the path. And the thing that we're interested in is, how do we describe these t hat and n hat vectors in terms of the x and y? So we may split up the force into these components. So let's consider the angle, the instantaneous angle this tangential vector makes with the path. So let's say we zoom in really close to the path, right? And the farther we zoom in, the more it sort of looks like a line. And that's going to be the angle we're going to be considering here. And you can see this would be some point lambda along the path, and this point right here would be some lambda plus some little differential, some d lambda. You can see that if we consider this lambda plus d lambda, then the path is going to shift a little bit based on some dx and a little bit based on some dy. And so we can consider the tangent of this theta, because we're going to be writing all our components with respect to this theta, and what we want to do is convert that somehow to be expressed in terms of lambda. We can do that by taking the tangent of theta, and this is pretty simple. So it's just going to be dy over dx, opposite over adjacent, right? And dy can be described as y prime lambda, or the derivative of y with respect to lambda. So anytime I denote a prime notation, that's going to denote a derivative with respect to lambda. Anytime I write a dot, that's going to be derivative of y with respect to time. So remember these two notations. We're going to be using both of these a lot. So y prime, so the derivative of y with respect to lambda, times d lambda, and that's the same for the x, and so you can see that this would be the same thing as y prime, the derivative of y with respect to lambda, over x prime. The lambdas are going to cancel out, so we're just going to be left with y prime over x prime. So that's going to be a relationship. Tangent theta is equal to y prime over x prime, and that's what we're going to be using a lot. Alrighty, cool. So I'm going to be let's move this. Oops. Hold on, sorry. For some reason my pen doesn't like me. There you go. So I'm just going to move this right here. So we'll have some space on the top right corner. So we can write something else there. Alrighty. So now let's try to describe this t hat in terms of this angle theta. So you can see here, it's pretty clear that we can write it like this. So if we consider the cosine of theta, it contains exactly cosine theta of the x hat and sine theta of the y hat. If you do not understand this, I'm sort of just deriving this based off of the definitions of cosine and sine of the unit circle, right? Because cosine theta would be the length of this triangle here, the base of this triangle, and then sine theta would be the height. And so this vector would just have x component cosine theta and y component sine theta, right? That's where I got that. And it's pretty clear to see that the magnitude of t hat would be equal to 1, because it would just be cosine squared theta plus sine squared theta, which is of course always equal to 1. So then, using this t hat definition, we can find the n hat pretty easily. So that's just going to be the same thing as t hat, except we're going to add a 90-degree angle to it, because remember, these are orthogonal to each other. So this is going to be a 90-degree angle. So it's just going to be cosine theta plus pi over 2 plus sine theta plus pi over 2. And however, these do also have very nice definitions. So the cosine theta shifted to the left, so you can think of the graph of cosine theta, and when we add pi over 2, it shifts the graph to the left by 90 degrees. And that's going to be the same thing as negative sine theta. And this is going to be the same thing as cosine theta. So that's what we're going to write here. Just going to cut everything here. That's actually convenient. Alrighty. So n hat is equal to negative sine theta x hat plus cosine theta y hat. So you can see that if we plug in, let's say theta is equal to 0, so t hat will face purely in the x direction, and n hat will face purely in the y direction, which would make sense. So let's say we plug in theta is equal to pi over 2. Then t hat will face purely in the y direction. So we're considering an angle of pi over 2. And you can see n hat would have negative x hat. So facing purely in the x hat direction and the left. So you can see how these two definitions definitely make sense. They describe our n hat and t hat perfectly based on the angle of the path. So those are going to be our definitions. However, we're not really interested in how we can describe t hat and n hat in terms of x and y. We are interested in how we can describe x and y in terms of t hat and n hat. So to do that, that's pretty easy to convert between the two. Because based on how they're written, it's actually very simple. So you can multiply this t hat by cosine theta. And then we can multiply this n hat by negative sine theta. And we just add them together. And what we're going to get is, the cosine squared theta plus sine squared theta. So hence, this is where I got the cosine theta and negative sine theta, because I'm making these relationships here. We're going to get cosine squared theta plus sine squared theta, x hat, and then we're going to get sine theta, cosine theta, minus sine theta, cosine theta, y hat. You can see this is just 0, and this would just be 1. This would describe x hat perfectly. This is how we would derive the x hat and y hat. So that's very nice. And I'm just going to do the same thing for n hat. and you may see for yourself. You may derive this for yourself. Let me just write this down. So we're going to get x hat is equal to cosine theta t hat minus sine theta n hat. We get y hat is equal to sine theta t hat plus cosine. That's very bad handwriting, I apologize. Theta n hat. So these are going to be our relationships we are going to substitute in. So this is how you actually resolve. There you go. I always click the wrong thing, I apologize. There you go. So these are going to be the relationships of x hat and y hat in terms of t hat and n hat. So this is actually how we'll be able to resolve the components of the force. This is going to be really cool. So now we're going to write our force on the particle in terms of this. So remember, the force of gravity was equal to negative mg y hat. Well, then this, if we substitute the definition for y hat, we're going to get negative mg sine theta t hat plus cosine theta n hat. You can see precisely what the tangential component of gravity is and what the normal component of gravity is. So then we can just, when we add the normal force to this, to get the net force, we're just going to cancel out that normal component. So we get the just purely the tangential component. So that's going to be great. So let's do that. So the net force, which is the same thing as mass times acceleration, so I'll just write this. So we know that mx double dot in the x hat direction and my double dot in the y direction, this is just mass times acceleration, is equal to the net force. So we have is negative mg t hat, so negative mg y hat, which is the same thing as this, plus, minus mg cosine theta n hat, and then of course we're going to have to add that normal force, which is going to be purely in the normal direction. So we know that the more the gravity pushes against the constraint path here, so if gravity was just pushing here, then normal force would have to cancel that out. Exactly. So this normal component and this normal constraint force would just be zero. They would have to cancel out each other perfectly. So all the motion is purely in a tangential direction, which is great. But now we have to write this left side in terms of lambda and in terms of the tangential and normal component. So we're going to have two components, a tangential force here and the normal force here. And we can just ignore this normal force because it is zero, is going to be constrained. So there is no motion in the normal direction. It's all purely in the tangential direction. What we're going to have to do is, of course, solve these x double dots and y double dots in terms of lambda, which is going to be a little tricky. But it's pretty much all just going to be the chain rule. So, for example, x dot is going to be equal to x prime, x dot. So x prime, of course, is derivative with respect to lambda, and then times x. Oops. Sorry, this is not x dot. I apologize. So the derivative with respect to lambda times lambda with respect to time. So we're just doing the chain rule here. So if we take another derivative, we're going to have to do the product rule. We're going to have to take the derivative of this with respect to time, which is just going to be x double prime, but then the lambda comes out. And since we already have lambda there, it's going to be squared. Then the next one will be x prime. So now we're just taking the derivative of lambda with respect to time. So this is just the product rule and the chain rule combined. And this is going to be the same thing for the y. And before we substitute this back in, we're going to just cancel out these masses. And we're going to substitute the x's. So what we get is x dot. Oops. So before we actually substitute the x double dots, let's actually substitute the components here and let's solve for a t hat. So you can see here that we're going to get m. So we're going to cancel out the mass. ms cosine theta. And what we're going to do is just group the tangential components and the normal components together. Then we're going to get sine theta here. Y double dot sine theta. So this is what I got after substituting the definitions of x hat and y hat, and then grouping the terms together for the n hat. Here we're going to get minus sine theta. You can see that everything I'm going to be writing here isn't really going to matter because we're just going to ignore the normal force. This is all equal to negative mg, where we cancel out mass. Negative g sine theta e hat. So we're just going to set the components equal to each other, and we're going to ignore this normal force because there's no motion in the normal direction. So all we're going to get is x double dot cosine theta plus y double dot sine theta is equal to negative g sine theta. So then what we're going to do is divide both sides by cosine theta, and you'll see that we're just going to get tangent theta, and we know the relationship of tangent theta here. So tangent theta is equal to y prime over x prime, and that's going to be certainly very useful. So let's do that. So this is going to be the same thing as x double dot plus y double dot, and when we divide both sides by cosine theta, this is going to be tangent theta, which we know is x prime over y prime. It was negative g y prime over x prime. Then we're just going to move the x primes. We're just going to multiply both sides by x prime, so we get some neat looking equations. Of course, I could have defined cosine theta and sine theta based on the magnitude of the hypotenuse here, but it would have just been canceled out anyway. So this is why I'm just considering the tangent theta. That way we have no mention of the length here, the hypotenuse. But then we're just going to reverse that step again and multiply both sides by x prime. So we're going to get y double dot y prime. It was negative g y prime. Perfect. Then finally we're going to substitute our x double primes that we just calculated here. So there's going to be a lot of steps to this, but the end equation is going to be a little nasty looking, but it's going to simplify based off of correct choices of the path, like x and y, whatever. If we're going to pick the circular path, you'll see lots of cancellation there. But this is just going to be the most general way we can describe constraint forces or constrained systems under gravity. So x double prime is going to be x prime double prime, and remember these primes are derivatives with respect to lambda. So the second derivative of x with respect to lambda, whatever x may be. Lambda. And then we know it's the same thing. It's virtually the same thing for y, is just with a y instead. Y prime. Oops. Lambda double dot y prime equals negative g y prime. So then what we're going to do is group the lambdas, the lambda squared and the lambda double dots together. So we're going to group the lambda double dots. What this is going to get us is x prime squared plus y prime squared, lambda double dots, and then we're going to group the squares, the lambda dot squares. This is going to get us x double prime x prime plus y double prime y prime. So as you can see, we have double derivatives and single derivatives, and then we're going to have a time derivative of lambda. So it's a lot of derivatives, kind of confusing, but hopefully the notation clears the confusion up a bit. We're going to have negative g y prime. And this is pretty much it. You can solve for lambda double dot if you wish in order to solve for these systems numerically, because I guarantee that for pretty much most choices of x and y, you're not going to be solving this lambda analytically. But you may, even though you see a lot of x and y's, just remember that this is all in terms of lambda or whatever parameter we choose for the path. So example, x prime, y prime, these are all functions of lambda. X double prime, all functions of lambda. So this is actually just a differential equation, a second order differential equation in terms of lambda. And that was pretty much our goal. How does this particle change? See, if we know how to describe the path parametrically with respect to lambda, our question is, how does the lambda change if it's subjected to a gravitational force, the particle? This is certainly very interesting, and what we get is this giant equation. And before I end off the video, I know the video is 20 minutes long. Holy crap. We're just going to make one little simplification, or one substitution. So let's just consider a pendulum path, for example. And I can write this in yellow. With a angle, let's just call it phi. So we don't confuse it with the theta that we calculate, that we used before. And this is the length, and this is the pendulum here. So this is the equation for any constrained path subject to the force of gravity. So we know how to describe x, which is just going to be the length. And since we're using this weird polar coordinate system, we know that the x is actually going to be equal to sine phi. Y is going to be equal to negative L cosine phi. You can see that if you plug in phi equals 0, then we just get y is equal to negative L, which makes sense. So y is below the axis, right? At L, at angle equals phi equals 0. So these equations certainly make sense. It's always important to do a gut check with these equations. And then we are going to take the derivatives of them. We get cosine phi, and then y prime is equal to L sine phi. And then we have to take the second derivatives because there are second derivatives here. So this is negative L sine phi, and y double prime is equal to L cosine phi. So then what we're going to do, so our parameter lambda is phi, of course. So we're actually figuring, it's just the replacement variable. You can think of this as sine of lambda, but we're just going to think of lambda as equal to phi. So because we usually use phi as the angle. So here you can see that x prime squared plus y prime squared is just going to be cosine squared plus sine squared. So you can see that this term right here is just going to be L squared phi double dot, right? And then this term right here, x double dot, negative L sine phi times L cosine phi. So you're going to get negative L squared cosine times sine phi. And then here you're going to get positive L squared sine phi cosine phi. You'll see that this term will actually just be 0. And then on the right side, you just get negative g, whatever y prime is, which is going to be L sine phi. And so solving for phi double dot, you get negative g over L sine phi. So indeed, this equation does work. Oh my goodness, I forgot to remove the line, I apologize. But you may see that this equation, so I just calculated, does indeed work for the pendulum system. We get the familiar pendulum equation here. So you may use this for whatever system you may like. Guarantee that you're probably not going to be solving for the lambda analytically. However, there's going to be some cool simplifications you can make if lambda happens to be the arc length or the distance traveled along the path, because here lambda is just some arbitrary parameter. It doesn't really represent anything other than a parameter used to describe the position. But if we call lambda equal to s, for example, we often denote s as the arc length along the path. And if you actually use the parameter s to denote the distance traveled along the path, so s actually does represent something meaningful, then you can actually get a lot of cool simplifications and stuff like that, and you can consider systems of space curves in a much more straightforward manner, and you can derive equations called like the I'm not going to get into detail here, actually. This is pretty much the end of the video, right? This video has already been 25 minutes long, so hopefully you guys got something from this. I will see you in the next one.